My name is Howard Johnson. I'm with Brocade Communications, division of Broadcom, and I want to welcome you today to the SDC 2021 virtual event. Today we'll be talking about fabric notifications, and I hope we have an opportunity to impart with you some exciting new developments in the world of fiber channel. And with that, let's get started. Give me a moment here to share the display. And there we are. Once again, welcome to the introduction to fabric notifications from awareness to action. This is Innovations in Fiber Channel, presented to you by Howard Johnson, Technology Architect here at Broadcom. What we're going to go through, first of all, is the problem and the solution associated with the fiber channel ecosystem and the development of fabric notifications, which I think is a very exciting technology. Certainly want to thank you all for participating in the SNIA Storage Development Conference 2021. Again, this year we're virtual, and hopefully soon we'll be in person, which is much more exciting and I think very useful for all of the participants at the SNIA SDC. In the meantime, let's take advantage of the great technology provided by Zoom, and let's have a wonderful virtual experience. As we go through the problem and the solution associated with fabric notifications, we're also going to discuss a few of the use cases about the deployment of fabric notifications. Just some examples going through how fabric notifications can be utilized in your environment by different devices, whether they're servers initiating I/O or targets as the target of the I/O initiation. There are some question and answer components in this presentation. We will not go through those during the virtual portion of the presentation, but I encourage you to look through these questions and answers. Many of these questions were brought out by viewers such as you who have seen the FCIA presentation on fabric notifications and wanted to delve a little bit more deeply into the components of this new technology. So now let's get started. The problem and the solution, the road to an ecosystem standard. This is something that the fiber channel community has been working on for quite some time. The standardization process began a few years ago, and we're wrapping up that effort pretty much as we speak. The fiber channel community got together, developed the standards, and then produced solutions that are now available in the marketplace. But let's step back a little bit and talk about what it is that we are after with regard to the problem that's being presented to us. The key problem has to do with flaky paths. That is, these are paths in a fiber channel deployment. Shown here in the diagram is a dual SAN deployment. You've got SAN A, SAN B. You've got servers who are connected to both of them to provide redundancy in their paths to these storage environments. And one of those paths is not behaving properly. That is, there are some physical errors that are occurring on the path, and the errors are occurring such that I/O will get through sometimes, but on occasion, the I/O is interrupted by these physical errors. These are persistent intermittent problems, if you will, that occur and that disrupt the overall flow of application data between the servers and the storage. What we have found in investigating these type of flaky path problems is that the multipath solutions have difficulty being able to determine when the problem is a physical problem or a logical problem. And the techniques that are used by multipath applications to resolve those issues are very much driven by their ability to send I/O and sense the responses to those I/O. This is an incomplete picture of what's going on inside the fabric, especially if you have a physical error that's associated with marginal cables, SFPs, or bad connections in the network. And what we have found while we investigated this particular phenomena is that multipath solutions have such difficulty with understanding what exactly is going on with these problems that their health detection mechanisms often create more problems than they solve. That is, that when the multipath solution is trying to figure out if a particular path is good or not, what we find is the performance tends to drop to almost near zero. The reason for that is because many of the path selections algorithms, which have evolved over time, we're still using a round robin mechanism of sorts. That is, they would send one IO down one path and then another IO down the other path. However, a lot of IOs are serialized. That is, in many applications, it's a read, modify, write type of operation. So the write operation cannot continue until the read is successful. If the read happens to fall down the inhibited path, then that read takes a long time. That is, the lower layers of the fiber channel stack will detect the error. They'll go through some retries. If the retries are successful, it just takes a little bit longer for the IO to reach completion. And then the next operation can continue down the other path, which will happen much more quickly. However, it's these retry operations, and oftentimes if the retries are driven back to the application level, they can take a significant amount of time, anywhere from a few seconds to 30 to 60 seconds, depending upon the nature of the impairment. And this is where the overall performance of the multipath solution is driven down to near zero, because we're waiting so long for the IO to complete in the first case before we can move on to the subsequent IO in the second case. So the real question now is that why has this particular problem come to the surface when it's on first look, it is something that would have occurred in previous deployments of fiber channel SANs. Well, a lot of this has to do with the fact that fiber channel solutions have become much more mature and diversified over the 2+ decades that fiber channel technology has been available. A lot during those early years were associated with fixing many of the basic issues in order to create highly resilient enterprise class solutions that fiber channel provides for storage infrastructures. We have now reached the point where a lot of those particular problems are solved, and now we're dealing with the more nuanced problems, such as the flaky path issue. Secondly, identification and mitigation tools have evolved over time. That is, there are characteristics now that are built into the components of a fiber channel SAN that help us identify these issues and allow us to surface this information up to the SAN administrators to more quickly identify and mitigate problems. And then finally, we have reached a point in time in the evolution of the fiber channel technology where customers are demanding more out of their solutions. That is, automation has become a key component to many technology solutions. And fiber channel is also one of them. That is, automation has become a characteristic that customers want to see in their fiber channel solutions. Putting all of these things together, the fiber channel community came together and said, hey, we needed to solve this particular problem. We need to utilize, that is, leverage the components that we have already in our systems. And we need to do this in a way that is much more automated. That is, when we don't want the SAN administrator to have to be involved in the identification, discovery, isolation, and mitigation of these particular problems. Basically, we want the system to heal itself. And in doing so, the community got together, delved into what precisely were the issues, and then came up with this new technology called fabric notifications. A lot of this technology leverages from other attempts to solve this kind of problem in other arenas, and picks off, that is, we cherry pick pieces of other solutions that are most effective and then let go of those elements of other solutions that were least effective. Most notably, the very simple idea that providing just an additional piece of information to the upper layers can help alleviate the problem without causing more issues. That is, by simply having the fabric tell the upper layers, hey, I've got a physical layer problem that I've noticed here. It's triggered one of my tools that has said only so many errors during over a certain threshold, and it sends the notification in band to the participating end devices. When the end devices know about this kind of issue, they can then surface that up to the application layers, that is the multipath solutions. And now the multipath solution has that one extra little bit of information that helps it understand precisely what the problem is. That is, they can distinguish between what's a physical layer issue, a logical issue, that is a device software kind of issue. So at this point, we're distinguishing between hardware and software problems. And also, it allows the multipath solution to determine whether or not the type of action needs to take place. That is, determine whether or not to completely isolate the path or just indicate that the path is in a marginal state and use it if there are no other paths available. So you can kind of think of it as, do I just take down the path in a hard manner and just say it's no longer usable? Or do I kind of set it on the shelf and say, hey, you know what, I'll use that path if I have no other paths available to me. And that's really where the power of Fabric notifications comes in. That is, we generate these notifications from the Fabric using the tools that we have, and we inform the devices of the particular impairment so that the existing software can take advantage of this bit of information and make better decisions about which paths to select through the Fabric. In our example here, we have SAN A with a link down to the storage, and it recognizes that the Fabric says, hey, this link's not healthy. In that particular case, he's going to generate an event that is the product of monitoring tools that have been looking at that particular link, and it's triggered a particular problem. For example, CRC errors. Let's say it's noticed that there have been 3 CRC errors in the last 24 hours on that link. And it says, you know what, that's a threshold that we're monitoring. And if we have more than 3 CRC errors on a link in a 24-hour period, we want to raise that notification up to our SAN administrator. In previous solutions, that notification simply was logged and an email message sent to the SAN administrator. And then he had to spend time figuring out which link that the message is associated with, identifying the particular applications that are utilizing that link, scheduling time to do the maintenance on that particular link, and then setting up a time to bring down the applications and performing the mitigation activities. Instead, with Fabric notifications, the switch simply says, hey, I've seen this issue, and I'm going to send that notification back to the server as well as to the storage devices to say that this particular link is having impairments along that link. In the notification, we have information that says the impairment it's exceeded the threshold of 3 CRC errors in a 24-hour period. The MPIO driver sees that particular notification and says, you know what, that link, that path, I am just going to put that as a marginal state. And I'll set it on the shelf and I'll use it if I have to. But meanwhile, I've got this other really good path that I can send my IOs down. When the multipath solution takes advantage of that particular piece of information, we see that performance restored to 100% of the system operation. The key component of all of this is the fact that we're leveraging the existing features that are available in Fibre channel solutions, and then adding an additional bit of information to applications, MPIO solutions that are available today, and allowing them to perform the activity that they're built to perform. The notifications provide a reporting mechanism. That is, they send events to the registered devices that want to hear about those events. They provide diagnostics. That is, the payloads include information about specifically what is going on, whether it's a link impairment kind of problem where it's an integrity issue, whether it's congestion, or just a case where a command has been discarded because of some other reason in the process of delivering the command from the initiator to the storage device. All of these operations are implemented through Fibre channel standard mechanisms called extended link services, and those mechanisms are utilized by the end devices. In addition to the notification mechanism, the Fibre channel community focused in on a particular problem called credit stall, where a link is suffering from a certain kind of a particular error, whether it's a device having an issue or the link itself having an issue and we've lost credit. And now the link is no longer able to perform at an optimal level. We can see that IO will get stalled. That is, it won't be able to be processed at line rate by the devices because of the lack of credit. Utilizing primitive signals, the Fibre channel community defined a mechanism that allowed the transmitter to be able to send a doorbell signal, if you will, that says, hey, I've got a bunch of frames here that you're not able to gather. take a look and see if there's something that you can do about it. If the end device realizes that, oh, I've got resource contention internally, he can take an action to alleviate that resource contention and eliminate the credit stall condition that's being produced by the device. Furthermore, the diagnostic characteristics that are available allow the transmitter to indicate which resource that his resources are being consumed by frames that have been destined for the egress device. Again, just to make note, the operation of this particular signal is done at very much at the link level, at the primitive level. And that's ideal because that allows us to drill through those credit stall cases where we can't send a more formalized message like an ELS. We can get a signal across that says, pokes the end device and says, hey, let's take a look and see how we can alleviate this particular issue. Just kind of to summarize where we've been with regard to the Fabric notification history, the Fibre channel community came together back in November of 2014 and began investigations in this particular problem. A lot of this had to do with customers coming back to the SAN providers and saying, hey, we see these issues. Every time we have an escalation associated with these issues, we get the SAN people involved, but we find out that it's more than just the SAN. There are some end device behaviors that are of concern. There's some storage behaviors that are of concern. Let's figure out what this is all about. The community came together and did some investigation and research along with various levels of experimentation to figure out what was going to be the most effective mechanism for dealing with these kinds of problems. Beginning in late 2018 and through 2019 and up to today, the Fibre channel standards community, known as T11, has been working on the solutions, and the end result were modifications to the draft standards associated with the Fibre channel framing and signaling. That's where the congestion signal mechanism is defined. That's that little primitive that acts like a little doorbell or wake-up call to an end device when credit stall occurs. The Fibre channel link services standard has been updated to define all of the notifications, the extended link services necessary to communicate the information associated with link integrity problems, congestion issues, and delivery notifications. And then finally, the Fibre channel switch fabric standard has been updated to provide the fabric detection and generation definitions to allow the Fibre channel ecosystem to deploy products associated with Fibre channel solutions that utilize fabric notifications. And just for a little bit of a reference, I'm going to walk backwards through each one of these standards and give you an idea of what's been defined in each of the standards. So for the switch fabric standard, it provides a fabric notifications overview and scope. That is, it describes exactly what's going to be utilized in the fabric to be able to generate the fabric notifications. And we define a brand new clause, clause 19, that goes through the error detection, signaling, notification, and registration mechanisms associated with fabric notifications usage. The one final piece that the Fibre channel community is working on is an informative annex to provide examples of how fabric notifications can be utilized and implemented by existing solutions. The framing and signaling standard is the one that defined the congestion signals, and it also defined a new timeout value called the frame delivery timeout, which allows the end devices to determine whether or not they are able to deliver a process of frame in a particular amount of time. Within the fabric, some people refer to this particular timeout value as the hold time. That is, how long can I hold on to a frame before I have to do something with it, either get it processed or discard it and have the whole transaction retried. That was real key to the fabric notifications mechanism because that provides the end devices with a way of being able to leverage the fabric notifications mechanisms to indicate that there was a timeout condition occurring because of resource contention. And by providing that bit of information back to the servers, they can realize, oh, my storage device is overwhelmed and I need to just back off, or that is pace my IO out to that storage device until he alleviates the resource contention problem and is back to normal operation. Again, these are all the kinds of mechanisms that are needed to produce an autonomous SAN operation. So just to walk through the highlights here, the framing and signaling standard defines the warning warning and alarm signal levels for generation of the congestion signals. It also describes the resource consumption mechanism that triggers the transmitter to send the signal. It provides an annex, an informative annex that indicates how congestion signaling can be utilized and how the mechanism actually works so that implementations can follow those mechanisms and create solutions of their own. And then finally, it defines the frame discard timeout value that would be utilized within the fabric so that the devices understand how long they can hold on to a frame before they either have to process it or discard it. Then lastly, we have the Fibre Channel Link Services standard. In this particular standard, we go through the detailed description of the what's called the Exchange Diagnostic Capabilities, ELS. That is all of these ELSs that are defined to allow the devices to communicate with the fabric and with each other about their current implementation of characteristics supporting fabric notifications. The Exchange Diagnostic Capabilities, ELS, allows the devices to exchange information on the opposite sides of the link to say, hey, my hardware is capable of doing X, Y, and Z. For example, my hardware can do congestion signaling, and I have the ability to detect congestion signals at 1 every 100 milliseconds, and I can transmit congestion signals at 1 every 100 milliseconds. Or the other side might say, hey, I also have the ability to do congestion signaling, but my hardware is capable of detecting them at 10 milliseconds and transmitting at 10 milliseconds. The two sides then understand what their capabilities are, and then they adjust their mechanisms, that is their detection and transmission mechanisms, such that they meet the characteristics of the other side. On the notification front, a new fabric performance impact notification, ELS, is defined, and a registered diagnostic functions, ELS, is defined. The registration mechanism is key to the deployment of the fabric notifications functionality because it allows the end devices to tell the fabric, hey, we support this functionality and we want to know about these issues. But that way, the fabric will never send a message up to the end devices if they don't support the function. So in order for the entire fabric to take advantage of it, all of the devices have to register, say, hey, I'm capable of doing this, and then the fabric will send the notifications out to the end devices when incidences occur. Finally, the fabric performance impact notification, ELS, is the key piece that is utilized, or this key command that is utilized for transmitting the information back and forth between the switch and to the end devices. Its payload has information about where the event was detected, what kind of event it was, what rule was triggered to cause the notification to occur, and also information about timing of those notifications. All of that information can be utilized by the end devices to determine what kind of automated process that they want to execute to alleviate that particular problem. And then lastly, there's an informative annex also in the LS standard that indicates examples of how to utilize fabric notifications in an environment, as well as how to deploy fabric notifications for particular devices. So let's just go quickly through a component summary. We have two components for fabric notifications. We've got the congestion signal mechanism, which is a primitive that can be sent from a transmitter to a receiver to help drill through credit stall conditions. So it's essentially saying that the resources at the transmitter are being consumed by frames arriving to it, and the transmitter is not able to push those frames onto its end destination because of a credit stall condition. So by utilizing that signaling mechanism, we can alleviate that particular problem. The notification ELSs, the exchange diagnostic, registered diagnostic functions, and the fabric performance impact notifications, those three ELSs are utilized to allow the entire ecosystem, that is the entire fabric, to be able to determine who can support the fabric notification functionality and to what degree they support it. The devices can also register specifically that they want to hear about specific types of events and they want to ignore other types of events. That level of flexibility built into the architecture allows the deployment of fabric notifications to come in smaller chunks, which eases its implementation into existing fabrics, allowing customers to absorb this new technology as the technology matures and becomes more readily available. So let's take a moment now and go through a few of the use cases in the 10 or 15 minutes that we have left. So the very first use case is very much associated with the problem isolation and determination. That is, what we're trying to do here is just simply reduce the amount of time that a SAN administrator spends trying to figure out where a link integrity or congestion issue is occurring. So in this particular scenario, the end devices, the servers and the storage, all they do is register to receive the Fabric notifications. And when they receive those events, they just simply log them. And now, inside those logs, depending upon the particular implementation, that may also generate, say, an email out to the SAN administrator or some kind of a trigger or some kind of a service operation that gets automatically generated as part of the full automation that a particular enterprise might have deployed. But again, the end devices are doing essentially the bare minimum. That is, register to receive them and log the information so that that information is there. The beauty of this simple addition to the Fibre channel environment is that the end devices immediately know when a particular problem is occurring. So if a SAN administrator or storage administrator, for example, realizes that there is a problem in their environment, that is, an application has gotten really slow, or they're seeing that particular servers are not getting the level of response they're expecting, they can look in the logs immediately, and then they'll see the Fabric notification event that says, hey, this particular link is suffering from link integrity problems, or this particular link is suffering from congestion problems. That bit of information immediately tells the storage administrator, for example, where the problem is, when the problem occurred, what rule was violated to generate the problem, and how often the problem is happening. Essentially, the SAN administrator has completely done problem identification, isolation, determination, and is only left with the mitigation activity. That saves many SAN administrators hours upon hours of time in dealing with these simple kinds of problems. So registration and logging, step one. That it will help your environment become much, much more resilient and reduce the amount of time that you spend trying to discover where and when particular problems of this nature have occurred. At the next level, we do link integrity isolation. That is, the end devices as well as the Fabric monitor both sides of the link to see if there's a particular problem. If, say, a storage device says, hey, this link here is not healthy, that storage device can actually send the link integrity event to the Fabric to have it distributed out to the servers. When the servers see that particular event, they push that event up to the multipath drivers, and the multipath driver now has the key piece of information that it needs. Hey, that IO is failing or being retried because I have link integrity events. Let me mark this path as marginal, and I will use the alternative path that does not have the impairment, and I'll maintain the high performance level that is expected by my customers. That particular addition to the Fibre channel ecosystem or your SAN environment simply allows the multipath solutions to work better. It allows them to utilize the knowledge that they have to select the appropriate paths, and it does this all in an automated fashion so that no SAN administrator intervention is required to alleviate the issue. The fact that the link integrity event is logged and noted, along with the automated mechanisms that are used by the end devices, allows the SAN administrator to schedule at a more convenient time the mitigation or the repair of that particular link. That is, they can go through and do the diagnosis to determine why they're seeing link integrity issues on a particular link at their leisure, rather than having it cause some type of an escalation in their type of environment. At another level, we could deal with target credit stall. This is what we're trying to do here is identify internally the resource constraints that can occur inside of a target, and to notify the initiators, hey, my resources are constrained. I can't push the commands on up to the upper layers. You need to back off. So utilizing Fabric notifications, the target device can detect that particular condition, send a Fabric notifications event to the Fabric, and then that gets pushed up to the servers. Servers then realize, oh, hey, I need to back off. I need to change my behavior in such that I don't want to overwhelm my target device while he's in a resource contentious condition. Again, this is all automated behavior that is triggered by the target device, the storage device, determining that his resources are being consumed. Similarly, the Fabric can determine when there is no credit on a particular link, and it can generate a notification that says, hey, we're seeing target credit stall here. You may want to back off or pace your IO out to the target device. Read over subscription is another issue that can be utilized and addressed automatically by the deployment of Fabric notifications. That is, when the Fabric determines that a particular server port is being oversubscribed because that server, for example, is asking for more IO than it can physically process on its link, the Fabric can generate a notification to the server and say, hey, you're congested. You're acting in a congested manner. Automatically, it can also send a notification out to the storage device that says, hey, this server down here is oversubscribed. The storage device can do a couple of things. The first thing it can do is say, you know what, maybe I'm operating at, on my port here at 64 gig, and perhaps that server port is operating only at 16 gig. So he looks into the Fabric, finds out what the operating speed of that server link is, realizes it's only 16 gig, and then the storage device can paste the IO back out to the server at a 16 gig rate, rather than blasting him with 64 gig of data at a time. Similarly, the server device can see the Fabric notification indicating that he's read congested and say, you know what, I'm asking for more data than I can consume across that particular link. I just need to reduce the rate at which I ask for data to a lower level, say dropping from 100% to just 90% or 85% of my ask rate. And immediately my performance improves. That is, my latency declines because the IO operates much more efficiently. Also, it's a benefit to the overall Fabric because that oversubscription condition no longer interferes with other servers who are also trying to get IO through the Fabric. That is, the victims of this particular bully flow, if you will, automatically are able to utilize the Fabric more efficiently because the bully flow has reduced its consumption of the resources in the Fabric. And as I noted, the reduction doesn't have to be severe. It can be in the 5, 10, maybe even 15% range of line rate, and immediately provide relief to all of the other flows in the Fabric. So this is a very exciting part of the ecosystem cooperation that's produced by Fabric notifications, as the initiators, the targets, and the switches all come together to produce optimal performance in the Fabric. Similarly, write over subscription can be handled in exactly the same way, just the process is reversed. That is, when write over subscription occurs, the Fabric can detect that and send the notification to the server saying, hey, that particular target port is oversubscribed. That server can back off a bit, and to help alleviate that particular problem, if there's a bunch of servers who are trying to get at that particular port, all of them are notified that that target port is oversubscribed, and they can all back off equally. The back off mechanisms just need to come down just a little bit, and what we see is the overall performance of the Fabric increases considerably and all of the devices run at an optimal level. Essentially, what's going on here is the fabric notifications mechanism is allowing all of the devices in the fabric to find this sweet spot of operation when all of them are requesting I/O through the fabric. And then finally, my final example here is the benefits to array-to-array replication. That is essentially the same mechanism that's utilized by the multipath functions in servers can also be utilized for storage devices when they're doing array-to-array replication. When a particular link is noted to have a link integrity problem, the arrays can be notified via fabric notifications that condition is occurring, and they can utilize the more healthy links between the arrays to optimize the replication process. So as we can see here, fabric notifications provides a tremendous mechanism for being able to improve the operation performance, resiliency, and health of the fiber channel fabric. It does this in an automated fashion, utilizing existing tools that are available in today's fabric solutions. Those tools provide just a teeny bit more information to the end devices, which is then percolated up to the multipathing or storage applications that can utilize that additional bit of information to modify their behavior to optimize their performance. All in all, the ecosystem has come together to solve the problem of persistent intermittent errors caused by marginal components, which is very difficult to mitigate by multipath solutions. It also allows the ecosystem to come together to alleviate congestion issues that ebb and flow in any type of fiber channel or storage infrastructure. The solution is quite simple. It's a notification mechanism and a signaling mechanism that is used to inform the end devices of impairments, and the end devices can choose when and how they deal with those impairments based upon the characteristics of their particular implementation. It is now a fiber channel standard. That is, the industry came together, put all of these concepts together, formulated the standard, and produced new drafts that allow the fiber channel community now to develop products that support these particular features. We've gone through a few use cases that give examples of the power of fabric notifications and how it can be utilized for your environment, and how devices can deploy this mechanism to alleviate issues in the fiber channel ecosystem. Also, if this functionality is available today, that's right. In a presentation like this, you might think that this is stuff that's way off in the future, but it's not. It's here today. Fiber channel switches support this capability, as well as directors and the HBAs that do the connectivity between the devices and the fabric. Operating systems are also supporting of this capability. IBM AIX, as well as Linux RHEL 8.3 support this functionality. The fiber channel community continues to work with other vendors as well to bring this technology into the mainstream, and we're very excited at where we are at this particular point in time. And here in 2021, we're delighted to see that this technology has become available in the marketplace. So I encourage you to go out and experiment and play with this new technology. But more so, I would encourage you to go out and buy it, try it, and see how it helps your environment. And before we wrap up today, I do want to thank the Fiber Channel Industry Association for the opportunity to present the fabric notifications component of the fiber channel community. The FCIA has been working in cooperation with the Storage Networking Industry Association for well over 25 years, and it's wonderful that the SNIA and the FCIA have this opportunity to work together and join forces on bringing out emerging technologies such as fabric notifications. And with that, I would like to thank you all for joining me today for the introduction to fabric notifications from awareness to action. My name is Howard Johnson. I'm a technology architect with Brocade, a division of Broadcom, and thank you for joining me at the SNIA SDC 2021.